Hi, my name is Sagnik, and for my final project, I will be presenting the paper Accelerated Mirror Descent in Continuous and Discrete Time, which is written by authors at UC Berkeley. And this paper is particularly relevant to our recent lectures where we started to bridge the gap between, some of those standard gradient methods and some of the more acceleration techniques that, we talked about maybe in the last week. So just getting into the motivation of the problem, why is it important? So throughout the quarter, we focused on gradient descent and projection methods, which converge at a rate of O of 1 over k. And this is quite robust, but it can be a little bit slow for large scale problems. So this paper introduces a framework that achieves a quadratically faster rate. It is at O of 1 over k squared. And what makes this paper unique is actually how they derive it. Instead of giving us, a complicated algebraic update rule, the authors are actually modeling this optimization problem as a physical system, specifically an ordinary differential equation. And this gives us a physics-based intuition for why momentum works. And also what this paper does really well is it's able to combine acceleration with mirror descent, and that allows us to, handle those non-Euclidean constraints very efficiently. So getting into the problem setup, what we're doing is we're solving, just the standard good old constrained convex optimization problem, which is, minimize a convex function f of x over a convex set x. And, we make the standard assumptions that the function's smooth, which means the gradient is Lipschitz continuous. But the key difference here is actually in the geometry of the constraint set X. In class, we often look at Euclidean constraints, say like a ball or a box. But this paper focuses on cases where the geometry is non-Euclidean. And, a very classic example for this would be the simplex, where variables are basically probabilities that sum to one. And, if you were to do a standard Euclidean projection onto a simplex, that would be very computationally expensive, and it would also be very geometrically unintuitive. So that's why we're using mirror descent, which is able to basically adapt the distance metric to basically fit our problem's geometry, right? Tailor it to the geometry of our own problem. And then, getting into the core algorithm, the authors actually got to the core algorithm by discretizing the ordinary differential equation. So they're essentially coupling two sequences, a primal variable x and a dual variable z. There are three key steps. So the first step is the dual update, which is where we update the dual variable z. And this step acts as our momentum. It accumulates gradients over time. And instead of just, reacting to the current slope, it's actually, building up the history. And then there's the mirror step. And this is by far the most important step in this whole process. Instead of just doing like a standard projection, we solve a minimization problem using a generalized distance denoted here as d sub phi. And this allows us to take larger steps that actually respect the geometry of our problem, the geometry of our constraints, if you will. And then we have our last step, which is that primal update, which is where we compute the new position x as a weighted average of this mirror step and the previous position. And then, yeah, just to discuss some, assumptions and guarantees here, you can ask, okay, what guarantees do I have? If I use this, what do I know for sure will happen? Well, what you know is that if the function is convex and it's smooth, and we, choose our parameters correctly, the algorithm will converge at a rate of O of 1 over k squared. And, that's exactly the acceleration we're looking for. We're looking to go from O of 1 over k to O of 1 over k squared. But there are some catches to this because the system here is actually representing a damped harmonic oscillator, which is like a spring with friction. And the momentum can actually cause the trajectory to oscillate around the optimum. So, once you get to the neighborhood of the solution, you might have to go around a little bit before you actually settle down. So this is where the trade-off comes in because yes, you get to the neighborhood of the solution much faster, but you're going to spiral around before settling, unlike maybe like a monotonic descent, where in the standard methods, you take a little bit longer to get to that solution, but once you're there, you won't spiral along as much. So yeah, I mean, there are trade-offs to this algorithm, but it obviously has that O of 1 over k squared performance, which makes it very appealing. And then, how does this link back to what we learned this quarter? This actually directly links to the material we covered in week 6, which is the gradient projection method. In class, we learned that the projection step is found by essentially minimizing that Euclidean distance, which is, finding the closest point on a straight line. And, we also solve these using KAT conditions. But The paper is actually generalizing that concept. The mirror step is simply just a projection where we replace the Euclidean norm with a generalized distance function, such as, the Bregman divergence. And, just like in class, the authors are also using KKT stationary conditions to solve these subproblems very efficiently. And, all in all, when you think about this, is that just mirror descent is really just projected gradient descent adapted for curved geometry. And then yeah, getting into that, some of these graphs over here, if you look at some of the experimental results, note that all of these are for when n equals 100. And, when you look at this figure, the black line is the standard mirror descent. It converges at O of 1 over k, and, the slope is very shallow. And then the colored lines are the accelerated methods. You see that O of 1 over k squared performance, which is, it's a much steeper slope, and this is just proof that it's just significantly faster. But if you do notice, as we mentioned before, there are ripples on that green line. And these ripples are basically visual proof of that oscillatory behavior that we talked about before. Once you maybe get close to the minimum, you do spiral around a little bit more. But that's just a small trade-off compared to the big old 1 over k squared improvement. So yeah, I mean, overall, just a much better method. And then, yeah, I do want to be upfront. I did utilize AI. Per the core policy, I'll acknowledge that I used Gemini to uh, help the format these slides in LaTeX. And I also outlined the script structure in LaTeX. However, I personally did all the math explanations, and I also did all the derivations. And I did definitely give a thorough read of the paper, but I will be upfront that I did use AI to help with some of the formatting and some of the overall organizational structure. So yeah, thank you for listening to my presentation.